the continuation of the previous lecture. In the previous lecture, we have solved these two problems, right? First one and second one. Now I'm going to solve all these problems, all these 10 problems. Okay. So third problem, yt equal to t mod xt. Okay. So we'll check the linearity condition first. Now this x of t is the input to the system. Now y of t is the output, that is t mod xt. T mod xt. I will give x1 of t as the input to the system. Say y1 t equal to, so from the above relation, t mod x1 t. x2 t is the input, then y2 t equal to t mod x2 t. Okay. Now I will apply the combined input a1 mod x1 a1 x1 t plus a2 x2 t as the input. Y3 t is t into input, t into mod of the input, that is a1 x1 t plus a2 x2 t. This is y3 t. Can I write this y3 t as t into a1 mod x1 t plus a2 mod x2 t? This is the question. That is a1 y1 t plus a2 y2 t, y3 t. So this is the question. Can I write like this? The question. We can't write because that y3t equal to, so some t a1 mod x1 t a1 x1 t plus a2 x2 t, this one is always, this one is always less than or equal to t a1 x1 t mod plus a2 x2 t mod, individual mods. Okay. So when it will become equal, when this a1 x1 t equal to a2 x2 t, when these two are equal, then only this equality condition holds. Otherwise, this is always less than this one. Okay. So I have already explained in the previous lecture this condition. Otherwise, I will explain here also. Let take for simplicity a1 equal to a2 equal to 1 and x1 t equal to, let us say, minus 3, t equal to, let us say, plus 6. I'm taking constants for simplicity. So this y3t equal to t into a1 is 1, x1t is minus 3, plus 8 is 1, x2t is 6, right? This whole mod, okay, is less than or equal to t into a1 is 1 mod x1t is minus 3, a2 is 1 mod x2 t is 6. Okay, so what is this value? This value is 3 into 6 minus 3, 3 mod 3 is 3. Okay, this is 3. So this is less than or equal to 3 mod minus 3 is 3, mod 6 is 6. So this is 90. This is 3t. Okay, so these are not equal. 3t not equal to 90, right? So this 3t is a1 x1t plus a2 x2t, it's t into, is not equal to a1 t into mod x1t plus a2 t into mod x2t is not equal. That is this y3t not equal to a1 y1t plus a2 y2t. So this is non-linear. Okay, because there is a operation on x, right? What is that operation? Modulus. So there is an operation on x here, mod xt. So if there is any operation on x, then the system is non-linear. Okay, and here the operation on t is there, right? T into mod xt. So it is a time variant. You want to check the condition? Yt equal to t mod xt. So to check time invariance condition, let us say xt is the input initially, yt is the output, that is t mod xt. Now I will apply a delay in the input. Okay, this is the input. What is, let us say y1t. What is the output? T multiplied by modulus of xt. So t multiplied by modulus of input. Input is x t minus t naught. Now I will apply a delay in the output yt minus t naught. What is yt? This is yt. Will apply yt minus t naught. Wherever t is there, I will put t minus t naught. This is the applying a delay in the output x t minus t naught. But y1t is not equal to yt minus t naught, right? So that implies time variant, because it is operation on t here. If at all there is any operation on t, then the system becomes time variant. Okay, next question. Next question, 4, 5 and 6. I will explain the linearity condition for one problem in 4, 5 and 6, and this is applicable to all these problems. Okay? Because there is an integration, right? Integration is involved here. So integration is a linear operator. Okay, so I will prove it. Yt equal to integral of minus infinity to t x of tau d tau, right? So linearity, and to check the linearity condition, same, xt is the input, yt is the output, integral of minus infinity to t x of tau d tau. We'll apply x1t as the input. Yes. Let us say y1t, that is integral of minus infinity to t x1 tau d tau. This is input. This is the output for input x1t. Next, x2t as the input, and y2t is integral of minus infinity to t x2 tau d tau. Now I will apply a1 x1t plus a2 x2t as the input to the system. Then y3t is integral of minus infinity to t. Whatever the input we applied, that input we have to put here in the integration. That is the relation they have given. So a1 x1 of tau plus a2 x2 of tau d tau. Right. Now I will expand this, because this integration, integral of minus infinity to t, this a1 x1 tau d tau plus integral of minus infinity to t a2 x2 of tau d tau. I can expand this because this is the integration property. a1 y1t plus a2 y2t. This one. So these are y1t and y2t. This y1t, this is y2t. So y3t equal to a1 y1t plus a2 y2t. So this condition satisfied. That implies yt equal to integral of minus infinity to t x tau d tau is linear. Whenever you find this integration operator or differentiation operator, then the system is linear unless there is no operation on x also. Here in x there should not be any operation on x square, x cube, root x, sin x, this kind of things will not be there. Okay, so this is linear system. Next, time variant or time invariant. This is important, how to check time variant and time invariant for all these three problems. I will explain for all these three problems. And a linearity condition you can easily check for other two problems, 5, 6. So these are the 4, 5, 6 problems. 4, 5, 6. So 5, 6 problems, linearity is same. Okay, these are linear systems only. You can check. Now, what problem? Yt equal to integral of minus infinity to t x tau d tau. I want to check the time invariance condition for this system. How to check? How to check? So, okay. First, I will apply xt as the input to the system. Then yt is integral of minus infinity to t x tau d tau. Now, I will apply a delay in the input, right? T minus t naught. Then let us say this is y1t, that equal to integral of minus infinity to t. So here from this relation only, here xt is the input, output is integral of the input, right? Here also from the same relation I am applying this input to the same system. This is the input, integral minus infinity to t, whatever the input there I will put that input here. X of, in place of t we have to put tau, tau minus t naught d tau. Okay. This is the relation they have given. Okay. From this relation only I have written this. Now I will apply a delay in the output, right? A delay in the output. This is y of t. This is the output. I will apply delay in the output. Y of t minus t naught, that equal to integral of minus infinity to, wherever t is there, put replace the t by t minus t naught. t minus t naught x of tau d tau. Okay, so these are dummy variables, not t. X of tau. So these are taus, not uh, they are not t. Okay, after integration, you won't get this. You won't get the function in terms of tau. Okay, these are just dummy variables. You can put any variable in place of tau. Okay, so whether y1t is equal to y of t minus t naught, that I have to check. So what is y1t? This is y1t. This y1t integral of minus infinity to t x of tau minus t naught d tau. Whether it is equal to y of t minus t naught. This is y of t minus t. I have to check. So, but to check this, here in the argument x of tau is there. Here in the argument x of tau minus t naught is there. So take tau minus t naught as some m, whatever, or lambda, whatever. So d tau equal to dm, and the limits also changed. So for these limits are tau limits. Tau equal to minus infinity to t. For tau equal to minus infinity, you get m equal to minus infinity. For tau equal to t, you get m equal to t minus t naught. The lower limit and the upper limits also changed. So this y1t equal to integral of, the limits are my m limits, m equal to minus infinity to, the upper limit become t minus t naught. Now x of tau minus t naught is m, d tau is dm, right? Now you can replace this m with again tau. This is dummy variable. So let us say tau equal to minus infinity to t minus t naught x of tau d tau. So now you can compare y of t minus t naught. This is y t minus t naught. Now this is y1t. Both are same. So y1t equal to y t minus t naught. That implies time invariant. Next, the fifth question, yt equal to minus infinity to 2t x tau d tau. You can easily find out from this equation itself. Here 2t is there, so operation on t. If at all any operation on t is there, then the system is time variant. Okay, so that we can check. I will give you proof also. Fifth one, yt equal to integral of minus infinity to 2t x of tau d tau. Same procedure. Xt is the input to the system, then yt equal to integral of minus infinity to 2t x tau d tau. Now I will apply a t minus t naught, a delay in the input. Let us say y1t equal to integral of minus infinity to 2t. So whatever the input xt is there, here that input will come under this integration. So here the input is this one. This input come under this integration with t replaced by tau data. Now I will apply yt minus t naught. This is yt minus t naught, a delay in the output. It is wherever t is there, replace t by t minus t naught, 2 t minus t naught x tau data. Right now, what is y1t? This is y1t integral of minus infinity to 2t x tau minus t naught d tau. I want to check whether this y1t equal to yt minus t naught. So to check this, first this x t tau minus t naught, this is x tau minus t naught, this is x tau. So let us say tau minus t naught equal to some lambda. Now d tau equal to d lambda. From this, these limits are tau limits. Tau equal to minus infinity to 2t. Now, if for for tau equal to minus infinity, we'll get lambda is also minus infinity, lower limit. Now this is the lower limit, and for tau equal to 2t, lambda equal to 2t minus t naught. Right? So now substitute all these things. Y1t equal to integral of lambda equal to minus infinity to 2t minus t naught. This is the upper limit. Now x of lambda d lambda. But this y1t is not equal to this y1t not equal to y of t minus t naught. These two are not equal. Okay? So it is time variant. You can clearly observe this from this equation itself, because integral of minus infinity to 2t is there. Here 2t is there. So operation on t. So that is why it is a time variant. And the sixth one. So there is no t here. Minus 2 to 4 x of tau d tau. There is no t. So there is no operation on t. So that is why this yt is time invariant. Right? There is no operation on t. So you can check yourself. Same procedure you can follow this. Seventh one. Yn equal to n into mod xn. So you can check the linearity condition easily from the second and third problems. These are second and third problems. So mod is there, right? So if at all any operation on x is there, then it is a nonlinear system. Here mod is there. Okay? Mod xn. It is nonlinear system. For eighth one, there are no operations on xn. Okay? For n greater than or equal to 1, xn is there. For n equal to 0, 0 is there. For n less than or equal to minus 1, xn plus 1 is there. There are no operations. Right? You can easily check the linearity condition using this. All 7, 8, 9, 10. No, not 7, 8, 9, 10 are linear systems. You can easily check the linearity condition. 7 is non-linear system. The time variant condition that I want to check. Seventh one is you can easily find out from third yt equal to txt. Similarly, yn equal to nxn. So there is a operation on n, right? Operation on n. So it is a time variant system. Okay. Next, in eighth, there are no operations on n, right? So it is a time invariant in the eighth question. There are no operation on n. And the ninth question also, there are no operation on n. The 10th question, yeah, here operation on n. It's like multiplying the signal by some other function n. First we apply n naught to the input, okay, x n minus n naught. This sine 5 pi by 6 n multiplied by x n minus n naught. But again, if you apply a delay in the output y n minus n naught, you have to replace n by n minus n naught. Sine 5 pi by 6 n minus n naught into x n minus n naught. That y1n, this yn minus n naught, both are not equal. Okay? So the system is time variant. You can easily check those things. Okay. Now stability condition. for all these problems. So the first one, yt equal to real part of xt. Suppose I will put this xt as m. Okay, in place of xt, I will put some finite value m. What is the value yt? I will get finite value only. Okay, so the system is stable. The second case also yt equal to mod xt. If I put a finite value in place of xt, I will get same finite value in place of yt. Okay, put m in place of xt, that is finite value. Then you will get mod m is also finite value. So the system is stable. But in case of third question, if I put m, that is x of t is this. If x of t is finite, that is, let us say I'll put m in place of x of t, t into mod m. Okay, so here, even though the x of t is finite, if t tends to infinity, what happens? If t tends to infinity for large value of t, it becomes infinite, right? So the system becomes unstable. It is not only depending on input, it also depends on time. Okay, that is why we are getting infinite output here. So for x of t is m, m may be finite, so y of t equal to t into some finite value. This m is finite, that's fine, but this t, I don't know what about this t. So t may be infinite, so minus infinity to plus infinity. Okay, time exists from minus infinity to plus infinity, or at least 0 to infinity. What happens at t equal to infinity? The system becomes infinite. The fourth one is important to check the stability condition. Stability condition. So yt equal to integral of minus infinity to t x tau d tau. Right. Now I will put in place of x of t some finite value. Okay. So integral of minus infinity to t x tau is some m into d tau. That is some finite value. Okay. What you get? Let us say m is constant. Okay. At m integral of minus infinity to t d tau. M, what is this? Tau. Limits are minus infinity to t. If you substitute this m t minus of minus infinity, right, you will get infinite. So it is not stable system, it is unstable system. Okay, for a finite value of input we are getting infinite output, so it is unstable system, not a bounded input bounded output stable. Okay. Next, integral of minus infinity to 2t. Okay, x of 2 d tau. This also unstable system, same condition. If in place of x of tau you put m, in place of x of tau you put m, you assume that this m is constant. Okay, then minus infinity to 2t, so constant into d tau, you will get 2t minus of minus infinity, that is again infinity. You will get again infinite output. So this is unstable system. But in the sixth question, integral minus 2 to 4, the limits are finite. Okay, we'll solve here. Sixth question, yt equal to integral of minus 2 to 4 x tau d tau. Now if I put x tau is some m d tau, okay, finite value, whatever the value, it is m. Okay, I'm putting some finite value. Let us say you take constant, m is constant, it is not a function of t. Okay, then minus 2 to 4, what you get? D tau. And you get 4 minus of minus 2, you'll get 6. Yeah, this is also finite, right? So because here the limits are finite, that is why we are getting finite output. So the system is stable. This one is stable. Okay? This one is stable. Before problems, the 4 and 5 are unstable because the limits contains infinite duration, minus infinity to t, minus infinity to 2t. But here the limits are not infinite duration, minus 2 to 4, finite duration. Next, here yn equal to n xn. Here n into mod xn is finite, that is some m, n into m. Here the additional constraint is there, the limits are from 0 to 10, 0 less than or equal to n less than or equal to 10. You put maximum value here, n equal to 10 here. So 10 into m, you will get 10m, that is also finite. Otherwise I will solve this. Yn equal to n xn for 0 less than or equal to n less than or equal to 10. This is the question. Okay, I want to check the stability condition here. So let us put in place of xn some m. Okay, yn equal to n into some m, right? And the additional constant is 0 less than or equal to n less than or equal to 10. And here xn is m. So this is the finite value m. If you delay by 1 unit, you also get some other finite value, right? You want to get infinite value if you delay it. Let us say some finite value, some f here, and m minus f. M is finite, f is finite. You will subtract these finite values, you will get some other finite value. Okay, this is what we are getting. But here n is multiplied by m. M is finite, okay, but the limits are 0 to 10, n limits. If you substitute maximum limit here, n is 10, 10 into m also finite, right? But in the previous cases, so t into xt, there there is no additional constraint on limits, so we can extend up to t equal to infinity. Here we can't put n equal to infinity here, right? So maximum I can put 10, and minimum 0 into m also finite. In between you can put any value, you will get finite value. So that is why the system is stable. For finite value of input, we are getting finite output. So the system is stable. Next, for n greater than or equal to n 1 x of n, you put m in place of x of n. X of n plus 1, you put some f for n less than or equal to minus 1. Anyway, it is 0 at n equal to 0. 0 also finite value. So here put m here, here some f. Okay, in place you're delaying x of n by 1 unit. You won't get infinite by delay. Okay, not by advancing. X of n plus 1, right? Advancing. So some finite value f, but in overall it is finite only, right? For n greater than or equal to some finite value m, for n less than or equal to minus 1, some finite value f. At n equal to 0, anyway it is 0, 0 is also finite. So entire output is finite for a finite input. So this is bounded input, bounded output, stable system. Next, the ninth question, yn equal to k equal to minus infinity to n xk. Okay, let's solve here. Yn equal to sigma k equal to minus infinity to n xk for finite value of input, that is sigma k equal to minus infinity to n. In place of xk, we put some finite value, that is some m, right? If it is m, if the m is constant, m sigma k equal to minus infinity to n is constant. How many points are there? So 1 plus 1 plus 1 plus 1 plus and so on, minus infinity to n, infinite points, infinite points. Okay, you will get infinity. So the system is unstable. Okay, unstable, unstable or stable is the correct word. Stable. Next, the 10th one, yn equal to sine 5 pi by 6 n, yn equal to sine 5 pi by 6 n xn. Okay, so what is sine theta? Sine theta value is always plus or minus 1, right? It will vary from minus 1 to plus 1. So that is finite value. In between, the value of sine theta is always lies between minus 1 to plus 1. That is finite value. But if we give x of n as some finite value m, this finite value, this is minus 1 to plus 1 into this em, you will get finite only. So that's why the system is stable. Okay. So the stability condition explained. And now causality. So for causal, this is simple. Causality and static and dynamics. For all these conditions are very simple. You have to check the feature inputs. Okay? Whether there are feature inputs. If at all you find any feature input, then the system is non-causal. Okay. So the first question, yt equal to real part of xt. Okay, are there any feature inputs here? Y0 equal to real part of x0, y1 equal to real part of x1, y2 equal to real part of x2. Always the output is depending on present. The present output depending on present input. Okay, so it is causal. There are no future inputs. First one. And similarly, second one also. Only xt is there. Mod xt. There are no any advanced things there. You have to check x of t plus 3 or t plus t naught. Any advancements are there in the x of t that you have to check. So here yt equal to mod xt, y0 mod x0, y2 mod x2, y minus 1 mod x minus 1. Okay. So these are all the present output depending on present input only. Okay. So system is causal. Here also yt equal to t mod xt. Okay. If I want, I will explain this. So yt equal to t mod xt. This is what is here. There are no x of t plus something, right? Feature inputs. Y0 you will get 0 into x0, you will get 0. Y1 you will get 1 into x1. Y2 2 into x2. It depends on y0 on x0, y1 on x1, y2 on x2. The present output depends on present inputs only. So it is causal. Next, fourth one, integral of minus infinity to t x tau d tau. Here also, so put y1 in place of t, put y1 minus infinity to 1, right? X tau d tau. And all the limits minus infinity to 1 are previous inputs, right? So this is depending on previous inputs, right? Or present input. At t, suppose y1, I will explain this also. yt equal to integral of minus infinity to t x tau d tau, right? Let us say y2 equal to integral of minus infinity to 2 x tau d tau, right? But here the limits are tau equal to minus infinity to 2. So 2 is a present value for the output, right? This 2. 2 is a present value, depends on present input. But the limits are minus infinity to minus 2, minus infinity to 2. From minus infinity to minus 1, all these limits are past inputs, not future inputs. These are past inputs. So it is a um, it is a causal system. There are no future inputs, right? That's it. Next, but the second case, and see yt equal to integral of minus infinity to 2t x tau d tau, right? So integral of minus infinity to 2t. Let fifth one. Let us say y minus 1. What you get? Integral of minus infinity to minus 2 x tau d tau. This is present input. This minus 2 is less than minus 1. So it is a past input, not future input. And minus infinity to minus 1 also past inputs for minus 1. Now let us say again substitute y1 here. Here you will get minus infinity to 2 x tau d tau, right? But this is 1, this is 2. So it is a future input, right? The future input, it depends on future inputs. That is why it is a non-causal, right? Fifth question is this is fifth one. Now the seventh one, to check causality. Yeah. So this is yn equal to n into mod xn. Here also there is no advancements in the signal. Okay, that we have to check. Any feature inputs are there. So y0 x0 y1 x1 y2 x2. Here also up to 10. You have to substitute up to 10 here. Okay, 0 less than n less than 10. Y0 x0 y1 x1 y2 x2 up to y10 x10. So present inputs, only present inputs are there. Present output depends on present input. Otherwise means remaining all cases of n. So minus infinity to minus 1 and 10 to infinity. In all these cases we have to see this signal, right? Only you have to see up to 0 to 10, this part. So in remaining cases also, so x of n minus x of n minus 1, right? Suppose some y of minus 1, let's say y minus 1 equal to x minus 1 minus x minus 2, right? So this is a present input for this present output, and this is the past input. Okay, so you won't get future inputs. You can take y of plus 1 also. You will get x of 1 minus x of 0. So 0 is the past input for y of 1. So it is always causal. Seventh one is causal system. Next, but eighth, this is eighth one, yn equal to xn for n greater than or equal to 1 and 0 for n equal to 0. So we'll solve this eighth one. Yn equal to xn for n greater than or equal to 1, and 0 at n equal to 0, and x n plus 1 for n less than or equal to minus 1. Okay. So for n greater than or equal to 1, yn equal to xn. You can check here. Then so n greater than or equal to y1 x x1 y2 x2. You have to check only for n greater than or equal to 1. That is 1 to infinity. N equal to 1 y1 x1 y2 x2 y3 x3 y4 x and so on. So the present output depends on present input only. So there are no future inputs for this case for n greater than or equal to 1. And for n equal to 0, okay, so y of n always 0, n equal to 0. Okay, y of 0 is 0. There are no future inputs. There are no x of 1, x of 2, x of 3 and so on. Okay, for y of 0. So it is here also causal. For n less than or equal to minus 1, that is we have to check up to minus infinity to minus 1. Let us say this condition. I am checking this condition here. Y of n equal to x of n plus 1 for n less than or equal to minus 1. Put minus 1 here. Y of minus 1 that equal to x of minus 1 plus 1, right? You're getting x of 0. But x of 0 is the future input for minus 1. Okay, so the system is non-causal. Or you substitute y of minus 2. You will get minus 2 plus 1, y of minus 1. Minus 1 is future input to minus 2. So system is non-causal. Ninth one, I will explain that also. Ninth one also. Yn equal to sum of k equal to minus infinity to n xk. Okay, so I will explain this like k equal to minus infinity to n minus 1 xk plus for k equal to n, I will substitute in the equation. So for k equal to n, this is x of n, y of n. Okay. So now I'll check it. Y of 0, k equal to minus infinity to minus 1, x of k, right? K equal to minus infinity to minus 1 means all these are past inputs. This is present. Okay. There are no future inputs. If you want, you can substitute some values. Substitute some 2, y2 equal to k equal to minus infinity to 2 minus 1, right? 2 minus 1 means 1. K y of 2 equal to sigma k equal to minus infinity to 1 x of k plus x of 2. This is present input plus 2 and 2 both are same, so this is present input. But here minus infinity to 1, these are past inputs because substitute all these things. K equal to minus infinity is a past one, and k equal to 1, x of 1, x of 0, x of minus 1, x of minus 2 and so on, x of minus infinity. These are past inputs, right? So there are no future inputs, so the system is causal. Next, yn equal to sine pi pi by 6 n xn. This one is also causal. Okay, so there are no advanced things here. X of n plus 3 x of n. Y0 x0 multiply with just the signal. Y1 x1 y2 x2 y3 x3, so is also causal. There are no future inputs. So this is how you have to check the causality condition. Okay, and the static and dynamic, that is memory or memoryless. Static means memoryless and dynamic system means memory. How to check? Just you need to check whether the system depending on past inputs or not. If the system depends on past inputs, then you can easily tell this system is memory. Okay? If the output depends on past inputs, means the system contains memory, right? So I will check memory condition for all these signals. I'll explain this just by seeing the question itself. Yt equal to real part of x of t. So there are no past inputs here, right? We already checked all these conditions, the past inputs also. Y0 equal to real part of x0, y1, x1, y2, x2. Only present inputs. There are no past inputs. So there is no memory. There is no memory means the system is static. This is static or memoryless. And this one also, there is no memory. There are no past inputs. Y0, x0, y1, x1, y minus 1, x minus 1, and so on. And this one also static. Y0, x0, t into x0. So y0, 0 into x0. Y1, 1 into x1. Y2, 2 into x2. Y minus 1, minus 1 into x minus 1. So it all depends on x, y0, x0, y1, x1, and so on. So only depending on present inputs. There are no past inputs. So with this integration, the integration involves minus infinity to t. Suppose y of 0 minus infinity to 0, that is minus infinity to minus 1. All these limits are past inputs, right? So it is a memory. Whenever you find these integrations and differentiations, those are memory systems. Okay. This yt equal to fifth one. Yt equal to minus infinity to 2t x of 22. Again integration is there, so memory or dynamic. Here also dynamic. If integration is there, the system is memory. Here yn equal to n xn for 0 less than n less than 10. But for 0 less than n less than 10, yn equal to n into xn. Anyway, here only present inputs are there. Y0, x0, y1, x1 up to y10, x10. Only present input. But here otherwise means, suppose if put y11, okay, y11 equal to x11 minus x10. So this is x10. This is x11. Anyway, this is present input, but this is past input. Okay, x11, xn minus 1 is the past input. So it is a memory dynamic. And here yn equal to xn for n greater than or equal to 1, 0, and xn plus 1 for n less than or equal to minus 1. Yeah. So for n greater than or equal to 1, only present inputs are there. Okay, x1, y1, x1, y2, x2, y3, x3, and so on. So only present inputs are there. Anyway, at n equal to 0, 0, you don't need to check this condition. For n less than or equal to minus 1, here you can check, put y minus 1, you will get x0, right? This is not past input. Put y minus 2, you get x minus 1. This is not past input. Okay, the future inputs, they are not past inputs. So the system is not depending on past inputs, so there is no memory, right? So that is static. There is no memory. It has to depend on past inputs. Then the system is dynamic. That is memory. It is not depending on past inputs. Only it depends on uh, present inputs or future inputs also. So it is strictly speaking, it is not static also, because so for static system, it has to depend only on present inputs, right? So it is depending on future inputs also. Okay, this I have to check once again. And ninth one, yn equal to k equal to minus infinity to n xk. So this I explained here. S1. Yn equal to minus infinity to n xk. So this is past input. K equal to minus infinity n minus 1 xk. This is xn. This is present input. So it is clearly depending on past inputs, right? So it is a memory system. This is memory. That is dynamic. Here yn equal 10th one yn equal to sine pi pi by 6 n xn. So here xn is there. There are no future inputs, only present inputs. In xn. It is a static system. Okay. So this is how you have to check the static and dynamic systems. Okay. Now I want to give some examples for invertible and non-invertible systems. Okay. So in this I will conclude this classification of systems. Invertible and non-invertible systems. Okay. What is invertible system? Suppose this is the system, right? Let us say some yes. This is yes is the system. I will apply x of t. Then I got a y of t. Okay. By any means, can I get from this y of t my x of t again? So this x of t. Is it possible to get my x of t again from y of t? If it is possible, this system is called S inverse. That is inverse system of S. Okay. So if it is possible, the inverse system exists for S. If it is not possible, the inverse system doesn't exist for S. Okay. So if it is possible for me to get x of t from y of t, then the system is called invertible. If it is not possible, that is, if my x of t cannot be recovered from y of t by any means, then the system is called non-invertible. Okay. We'll give some examples how to check the condition. Okay. So two conditions are there. One, suppose for this system I am applying x of t. Okay, let us say y of t is the output. For any non-zero input, suppose if x of t is not equal to 0, for any non-zero input, I am applying this input to this system. If I get 0 at the output, for any non-zero input, if I get 0 at the output, is it possible to get x of t by any means from 0? If I apply 0 to the any system, can I get some non-zero output? Here x of t not equal to 0. This is what we want, non-zero input. Can I get the same thing here? This is non-zero, right? To give 0 is the input to the system. Can I get a non-zero output? It is not possible, impossible. Okay. So the first condition you have to check is for any non-zero input, whether we are getting 0 output. Okay. So if we get 0 output, it is non-invertible system, because from 0 you can't get your original signal x of t by any system. So here S inverse does not exist. This inverse system does not exist for yes, it is non-invertible. This is one condition, and one more condition also there. Second, suppose this is x of t, y of t, okay, system. If multiple inputs gives same output, that is if x of t gives y of t, and suppose some x or otherwise we'll take okay some x2 x1 some x1 of t also gives the same output y of t. Now I want to recover original signal, okay, from S inverse. Is it possible? Here I don't know if this is at the output. I don't know this is x of t or x1 of t. I don't know. So there is a ambiguity. So it is not possible to get exactly x of t or to get exactly x1 of t. I don't know this is. So we need to get the unique input at the output of the inverse system. Here it is x of t. Here also it should be x of t. I don't know. I can't guarantee that it is x of t. It may be x1 of t also, because for x1 of t it is the output y of t. I will give some examples, then you will get some clarity. Okay. So first one, yt equal to x square of t. Okay. First one. So this is the system xt. Okay. Let us say s. You got yt. This x square t. Right? Now I will apply to some inverse system. I have to get x of t. Is it possible? That I have to check. See, suppose I will give minus xt here. Okay, for the same system, I will apply. What you get? Y of t equal to, this is y of t equal to input square minus x of t whole square. You will get x square of t. Right? You are getting same output here, right? So for x of t, output is x square of t. For minus x of t, output is x square of t only. But what you get here, if you apply, let us say this is x square of t. This is the output. What you get here at the output? Let us say I will apply square root system here. S inverse is square root. What you get here at the output? Square root of x square of t. That is plus or minus x of t. I don't know it is plus x of t or minus x of t. Okay? This is not unique representation. So it is not invertible system. It is non-invertible system. We need unique representation of x of t at the output of the inverse system. Okay? So therefore non-invertible. I'll give one more example. Yt equal to sine of x of t. Yt equal to sine of xt. So if I give input xt to the system, we get y of t equal to sine of xt. For non-zero value of input, let us say xt equal to some I. This is non-zero input. I am giving this input to the system. And what is yt? Sine of x of t. X of t is pi. What you are getting? 0. So is it possible to get again x of t from 0 input? Okay. Can you get an inverse system to get from 0 input to get the x of t? Is it possible to get x of t from 0? So is there any system to give a non-zero output for a 0 input? No, not possible. So inverse system doesn't exist. Item plus non-invertible. So you have to check these two conditions. So the first condition is whether a non-zero input gives 0 output. This you have to check. And the second condition is For multiple inputs, same output. Okay, so these two conditions we have to check. If these two conditions are true, or any one of them is true, then the system is non-invertible. Okay, otherwise invertible. Okay, so with this, I concluded the classification of systems, and I want to summarize. Okay, so give summary of this summary to check. The first one is linearity. What to check for linearity? Check operations on xt input. This is we have to check linearity. And second, if the operations on xt are there, then the system is nonlinear. If not, then the system is linear. And check time invariant and time invariant conditions. Check operations on t. Those operations are scaling or time reversal. These two. Not advance, not delay. Okay, they won't change the time invariant property. And third, causal. What we have to check? Check whether future inputs are there. That we have to check. If the future inputs are there, then the system is non-causal. If not, it is a causal. Next, fourth one, stable. The stable, as usual, the procedure. Apply finite input. Apply finite input. Whether the output is finite or not. This we have to check. If it is finite, the system is stable. If it is not, it's stable. Static and dynamic. Check whether past inputs are there. Okay. So if past inputs are there, then the system is memory, that is dynamic. If not, static. Okay. So all differential and integration equations are memory systems. They contain memory. Six, invertible and non-invertible. These two conditions. We need to check two conditions. First one is whether a non-zero input gives zero output. This we have to check. or whether multiple inputs give same output. In these two conditions, we cannot recover the original signal exactly by any means. So in these two conditions, the inverse system doesn't exist for a system. So the system is non-invertible system. Okay. This is the summary of classification of systems. So with this, I concluded the classification of systems. Okay. You practice all the problems on this classification of systems, then you will get clarity.